Okay, thank you for having me. I'm going to talk a bit what we do in our group, and I'm also going to mention what a study we have done on kids recently, last 2 years. So the title of this talk is Brain MRI of Moving Pediatric Patients Using Prospective Motion Correction and Fast Sequences. And this should summarize what I'm going to tell you today. Here's us. I usually want to start with who we are, so you can see if you recognize us. We are 7 people in our group, and we are working, basically our day goes by programming MR scanners and making pretty images of the brain. What makes us a bit different maybe from other researchers is that we're very close to the hospital, but close to action. We are sitting next to radiographers, next to the neuroradiologists, so we are very sort of mixed up in our daily life. So everything we do goes to radiographers, and we try to implement new techniques. If they're not good enough, we're going to be criticized for that, and then we're going to go back and improve them, and so it's like a cycle for us to. Eventually, we are able to make something that's useful, and then it goes out to the clinic on patients. We know that MRI is a slow modality. We have long waiting times usually for an exam slot. It's also around sort of referring hospitals. You usually have some reluctance to refer a patient to an MRI because the CT is faster. It might try other methods because MRI is considered slow and time consuming. We know also that long exam times is associated with MRI. It usually takes like 20, 40 minutes. You need to scan many times, many series per an exam and so on. We also have MRI scans, exams that can take 2 hours. They do exist. They're not that common, but they do exist. And each scan takes several minutes, and that is the key for why MRI is a problem. We are making images where we expect the victim or the patient to be still for 2 minutes, 4 minutes, or 6 minutes, something like that. And we can't do that with a regular camera. We cannot do it with an MRI scanner either. So here's how the images look if you move. Many of you who have seen into MRI, you know that this is sort of very, very common. It's very common for patients with claustrophobia, pain, brain damage, Parkinson. There are a lot of different types of patients you can think of on adults. But for children, and at least at our department or our hospital, from 3 years of age, we usually use general anesthesia. We knock them out. And with that comes, it takes time to make them to sleep. We need to reserve the MR scanner for a couple of hours. We need to book it for 2 hours because we don't really know exactly when the patient's going to arrive. And there's also a wake-up time for the hospital. You need to wake up the kid and take it home. Below age of 3, we usually have a nasal spray called Dextor. Knock the mouse with a lighter sedation can be administered by radiographers. But also associated with time to sleep. It takes some time to take them down, and we also need to reserve the MR scanner for longer, and you need to carry home the child usually, so you cannot use it for older kids. Sedating children, it's costly. It requires longer planning ahead, and that's why I have the calendar icon there. And it takes longer time. You see these hours it should take maybe 20 minutes. It takes like up to 2 hours to reserve time. And it's also not risk-free. I checked with clinicians at Karolinska, and they say that every year we have some light incident or small incident of anesthesia. And every few years, every 4th, 5th year or something, there is a brain damage occur of some sort due to anesthesia. It's very rare, but it can happen. Here is statistics from last year. When you can see to the left, you see 3 histograms showing the time. Someone has clocked the time it takes to put the child to sleep before an MRI, and the average is 20 minutes. Could be up to over an hour. And then MRI time is an average or median of 42 minutes, so it's getting up to an hour. But that's just the effective time. You still need to book it and reserve the MR scanner for much longer. And then you need to have the wake-up time as well. To the right, you see the waiting time for MRI in days. And as you see, most of the patients do get their MRI within a couple of months as a peak, but they have a long tail, and some of them, they can get an MRI maybe have to wait for a year. And that is not great, obviously, because that's a consequence of reserving the scanner for too long times. You can get through fewer patients per day. I also want to say personally that if we can make techniques work without anesthesia, I think anesthesia should be reserved for sort of when you put something sharp inside the body, because then you need anesthesia. MRI itself is a safe technique, so we really should try to avoid it. We have two major themes in order to get the MR scanner to work faster for us, and also try to avoid the anesthesia problem for children mostly, but also for some adults. We're going to focus on children here today. Theme one is to go ultra fast. Ultra fast is a very vague word, but it means that we try to come up with new ways to do an MRI scan in a quick way. And we developed a sequence. Sequence means that a sequence is MR jargon for imaging strategy, a plan how to make MR images. So if you hear me say pulse sequences or sequences, it means that a way to make images. Neuromix is a pulse sequence we made a few years ago. We have used this now in the clinics in daily routine. We got the scan time down for about 30 minutes equivalent for these images, down to like less than 3 minutes. I'm going to show you a bit of that. The second theme is to do real time, or prospective is another word for that, motion correction, PMC, prospective motion correction. The idea here is to have some kind of sensor near or on the patient, so that will sense how the head is moving in real time and inform the slow image acquisition, so the slices are following the patient real time. And these times need to be very short from the action to updates. This order of tens of milliseconds is necessary. But you see the basic idea that to the bottom right, you see slices and patient moving his left head back, and the slices are supposed to follow. Because you know, each set of images takes several seconds or even usually several minutes to acquire. And then you have to be able to follow in real time the head. We have made a device called RAD. I'm going to show you a little bit of that in this talk. We put on the patient's head. Theme one, ultra-fast brain MRI. The idea was for us to make a single scan button push. It's actually not the button like this, but the idea is you press scan, and then all sequences you need, all image contrast. MR can do many types of images you need for an MRI that should be done directly for you without pauses. We can do this in 2 minutes and 39 seconds now. This is just for you to understand our world a little bit, not that you're going to go through it in depth, but basically, when we do this kind of complicated imaging technique, we need to spend years on making new software. We can't just use the vendor's software. We need to make a different sort of Lego blocks, type of sort of modules that we can then build upon, and then make all these complicated waveforms to the right. And these waveforms to the right are just different strategies to acquire an image that produce images that look differently. So now we want to make one technique, Neuromix in this case, that will do them all in one go. Here you see a single slice. Here's a kid, as an example to show you that this sequence can do lots of different MR images for different needs. For instance, you have text at the top there showing roughly what the main benefit of that image type is. So image contrast, you have to the top left, you have T2 weighted for fluid, you have T2 flare for inflammation, in DWI for infarcts, and T2 star for bleeding, and to the right you can have tumor blood detection. At the bottom left you see SWI image for microbleeds, and to the bottom right you see one volume we acquire, T1 weighted for the same reason as the top right. So basically these are and you can see the times there in seconds, how many, or 17 seconds or so, for how much time each model takes, but they all run together without interruption. You press only once, so you can get full brain coverage. And thanks to we have all these different flavors of MR images, we can usually see most stuff in the brain. regardless of the question. We also have downloaded this. Very nice people around the world. Sometimes there are people giving out software for free. We have downloaded this software from this website, Pierre Coop. He has shared a denoising software. It's not AI, but it's non-local means. You can just take the top row and denoise that in the reconstruction, and then you get the denoised image in the back. I don't know if it shows up, but it definitely shows in PACS if you look on it for real. This makes, since we go so fast, we don't have time to capture enough signal all the time. So we need some image become a little noisy, and then we can use denoising methods to combat that. The important thing is that we can get different types of images that we see different things. Here's an example from May this year. There was a patient came from another hospital in ambulance, and maybe she was 1 year old, 2 year old. I don't remember. Very young, at least. That patient was too unstable for anesthesia. They start scanning the image to the right with conventional MRI. As you see, at least especially from the image at the top right, you can see it's not great, right? It's very blurry. The patient is moving. They cannot knock the patient out with any medication. I happened to be there, and we have proposed we should do a neuromix, and those images you see to the left. The images to the right are blurry and took like 20 minutes to acquire. And to the left of the blue bar, you can see the neuromix cocktail, about 3 minutes worth of scanning. And since we're so fast in this case, we are getting you're not sensitive to motion. You see a lot on this image. At the bottom in the blue dash box, you can see a small bright dot from an infarct. Can you see that? Do I have a laser here? Here? Oh, sorry. Here. There's an infarct. Up here you see something else. And here you see, on the theta flare, you see, I don't know what it is actually. Maybe you can tell me. But at least the point here is that there are different things. Here's a bleeding. You see different things. So each of these images show different things, and this sort of I think it was some sepsis or something. There was a lot of things going on in this patient. I haven't read up on the details, but what I can tell you is that with this neuromix, we can at least try to capture a lot of different pathology in one go. We also share this technique to other sites. Everyone who wants to have this sequence, we share. So here are the dots, 29 sites in the world. Right now, we share it since January 22. So legally, they're not allowed to use it in clinical routine. They sign off that they're not going to sue us. They're not going to sue GE Healthcare. But everybody seems to be sort of happy. I think some are using for research. Some are using it on patients. But we just give it out, and then we get some feedback sometimes. So that was theme 1, to go really, really fast. Theme 2 is to do real-time motion correction, or PMC, prospective motion correction. The idea here is to track the patient's head in real time. Then you don't need to go so fast, but you need to do some other things. Here's Adam in my group, Anna van Niekerk from South Africa. He has developed his wireless radio frequency acquisition device. Very boring title, a boring name, but that sort of spells out to be called RAD. But we have chosen this name for some reason, and now we're stuck with it. So just when you see this device, it's called RAD. It's not a good name, but anyway. It has at least been improved a lot over the years, and now we have in an enclosed form with a minion-looking figure that you can put on the patient's head. This device, I won't be able to tell you the details because this takes a long time, but it basically, you see here, you see RF pickup coils that senses the, you get the RF pulse, and also these coils here also senses the MRI gradients in X, Y, Z, so it can figure out where it is in space. It also figures out, it has a gravity sensor and also have magnetometer sensors, so it can know which direction is down, which direction is into the scanner, parallel to the bore. And then with this rate of change of the gradients, it will know where it is in position in space. So you can get all directions of motion you need. You need 6 parameters for finding out where the head is in space. You put this on the patient's head, and then it will report back by sending Wi-Fi back to, like, I think I have it here. It will, yeah, so here's how it looks. You put it on the patient, it will send our Wi-Fi to a wireless receiver here, goes Ethernet back to the MR equipment room, which updates the gradients and which is connected obviously to the MR scanner. So this is basically how it looks in action. Can I click this? Does it work? No, it doesn't work. Okay. Maybe I need to move here. How would I do this? Oh, yeah. Okay, cool. So here's how it looks when codec unavailable. Here's. Okay, this didn't work, as usual with PowerPoint. But here's a kid. It's a real kid moving, but she's still now. She gets this device on her head and just goes into the MR scanner. This works at least. This is important. Before we continue, let's think about why Cartesian 3D sequences are hard to correct for large motion. And Cartesian means just regular standard MRI. You acquire MR images in a grid type of fashion. 3D MRI is very popular. It's very popular because you can view it afterwards in any angle. But the problem with 3D imaging is that it's very hard to combine that with large motion. I want to focus you, if you want to look at one thing here, I want to focus to the bottom left, nodding motion, which is most prevalent, most common, and compare that with the top left, no head motion. You can focus on the left part, if you would. You can see in both cases the magnitude, the grayscale image here is fixed, because in this case, the patient is fixed, and here we are tracking, so that it appears to be fixed. The problem is that in MRI you also have not only the magnitude signal, you also have the phase signal. So this is how the brain, this is the content of the brain changing the magnetization inside the brain. Without you taking any image or not, it changes when you move, when you nod, because you're breaking the feed lines. The feed lines are coming here through the tunnel, and with your position of your head, you're breaking them in a different way, so you're going to change the magnetic field inside the brain. And if you do that, when you move, you can track it, so the slides are following the head, but the content inside the head is changing no matter what. When you try to combine that into full 3D image, when you do normal standard vanilla MRI, it doesn't work, because what you end up with is, I'm going to show that in the next slide. So if you assume that you have a perfect prospective motion correction method of some sort, the magnitude image, the grayscale image, which you usually look at, is going to be stationary, and under head motion, it's going to be sharp without problems. But that is only if you don't have a 3D sequence. If you do honor that the phase in image changing due to head rotations, then each, the raw data in MRI is called K-space, and they will see a different type of head every time you acquire part of the image. And that's going to be like a cocktail of different magnetization, and you're going to end up with rubbish. And rubbish is more specifically looking like this. This is a still image, SWI 3DPI. Here are our new sequence for motion correction project called sequential 2D EPI, SWI. Look how, when it's still, both are good. When you move without updates, without motion correction, or with motion correction, it doesn't really matter. With updates, the image are correctly located, and without updates, they are not corrected, but it doesn't matter. They are equally bad, because the contours of the head has changed. Whereas if you go for snapshot imaging, you can avoid that. For us, we have 3 layers of protection against head motion. The first is acquisition. We do prospective motion correction using this device, RAD. With prospective motion correction, we can use this RAD to make image planes to follow the patient head with only 5 to 10 milliseconds delay. So from this motion is happening, we can correct the slides within about 5 to 10 milliseconds after it has happened. What we cannot do is to be 100% accurate. We can be fairly accurate, but not 100%. We can also we can remove this spatial temporary. We cannot remove this phase that I talked about. So defense layer 2 is to have another type of acquisition, another strategy to how to acquire MR images. We want to rely on single shot techniques, which sort of like a normal camera, freezes the motion. That has drawbacks with you can't go so high in resolution and so on. You can have either EPI or single shot fast echo techniques, which are also embedded in NeuroMix, for instance. We can also use propeller multi-shot techniques. Propeller is what the sort of this raw data trajectory for use, those of you who are familiar with MRI. Basically, each of these blades are making a full image, sub-image, which you can, it's too advanced to talk about it today, but it's one of the few ways to acquire MR images in chunks and build them up together without to have this problem with the phase problem I had said before. Third line of defense is image reconstruction. After you've got the raw data and you reconstruct it to regular images, sometimes you have several sub-images you can realign in the reconstruction process. For instance, diffusion-weighted images are usually you acquire several diffusion directions. In this case, we can say we have 6 different diffusion directions. We can align them in reconstruction image domain before we average them. We can also, for this 2D SWI sequence we have done, we can do we can realign them before averaging and so on. Our pediatric brain protocol, to the left you see some publication we have done. We have 2 with the Tracolin systems and 3 with our own RAD device. But basically we try to make new software and hardware for combating this problem. Here's a protocol. It's a few sequences, but mostly this is maybe more considered like a selection you can choose from. We're not going to run all of them. For instance, we're going to kind of heavy on the T2-weighted images here. We have 4 of them. This is discussed in collaboration with our radiologists. We usually run only 2 of them. Coronal T2 flare propeller with the RAD has been very popular, and so on. But we always run the NeuroMix in the beginning, because if the patient stops to accept the scan, we have at least done 3 minutes worth of scanning and got sort of decent kind of images anyway. So this purple space is, if you expand that, you can see that we have all these different contrasts. We have T2, T2 flare, SWI, T1, T1 flare, and diffusion inside NeuroMix as well, some slightly low resolution. We have also, as you see here, the scan time, and you see scan time with acoustic reduction. We have started to making the scan slightly longer because we want to make the scan and make less acoustic noise. We have seen that some kids think it's too frightening to be when it's too loud. So this is basically the things we have done for our study. We have done 62 children. We have scanned children from 3 years of age up to 9, mostly 5, 6. Requirements is that they can communicate. We have the light autism kids, but not the strong autism kids. We have required them to say no, they don't want to be there. So we have chosen 3 years of age because we want them to be able to be absorbed enough by a cartoon movie we show to them. We have the target MR protocol duration for 20 minutes. We have said that we have reduced in this year, midway through the study, we have made the scanner like 10% slower. And by that, if you see what your MRI people know is you're slowing down the gradients here to make it quieter. But what you get is some more distortion in the front of the head here. But it has been sort of a trade-off we're willing to make it more pleasant for the children. We also wanted them to go here for the first time. We have chosen to just be able to, we wanted them to be able to send a letter to them, to the parents, saying you're welcome for this exam, and try our best to make it work at first sight. And then we realized that was not always working so well. So we have then in this year we started to spend a week on making videos, prep videos for the children. I will show you, hopefully, if it works. Yeah, the children is watching at home before they arrive. And let's see if this works. Is it on the screen? Okay. Oh, yeah. Here's us also being a bit creative. 4 of the kids we have scanned didn't want to go into the scanner, so we put the mom inside as well, or the dad. In this case, it was the mom. So this is kind of an effective way to, without any sedation, to do full MRI. The mom is just holding the child below the RF coil, and that works pretty well. It's not super nice for the parent, but the parents are very motivated. And if you're a very fluffy parent, maybe it doesn't work, but it has been working quite well so far. Okay, so here's some results. Patient, 8 years, Neuromix at the top, our motion correction, prospective motion corrected sequences at the bottom. At the bottom you see more high resolution. These are a bit small in text here, but you can see -10 to 2, -12 to 5. It's basically 15 degrees of head motion in these cases. Another 5-year-old, this 5-year-old had Apert syndrome. She moved a little bit more, I think about 20 degrees. What's interesting when you move so much is that the cerebrospinal fluid is like shaking like a mixer, so it's just kind of turbulence. So you see the white here is actually from CSF flow just running around. It's not pathology. Here is one that I like to show because this is 33 degrees of head motion. Peak to peak. If you look at this is a single T2-weighted coronal scan to the right. This is how the images ended up. This is the motion trajectory you see that actually happened during those 180 seconds, 3 minutes. See if I can. Can you see the arrow? No. Sorry. Okay, I want to go there. Yeah. So this graph has been converted on a doll here to show. If you appreciate here, maybe easier to appreciate how much motion happens. So if you look at the blue, you can look at the head. This is actually how the patient was moving in real time. This has not been. There's a lot of motion here going on. And I want to show with this orange bars I'm a bit of a thumb sucking here a bit, but you see a few millimeters, a few degrees is what normal MRI can handle. About that sort of region, MRI image becomes bad. And if you move this much, this is a coronal image of myself when I'm trying to mimic the same amount of head motion that occurred for this patient. So this is to the left is me moving as the patient to the right was moving, but without updates. So it's really, it is possible to correct for this. Here's the last, one of the last few slides here. Another 4-year-old patient we scanned last week. We have 3 sections here in the motion plots. So what you see here is the head nodding in rotation. This nodding motion is the most prevalent. The first one is 36 degrees of head motion. The Neuromix in the center is 38 degrees. And the third one is T2 propeller, 2 millimeters, is 42 degrees of head motion, which is a lot. It's more than the last previous one. And still we are able to make this coronal T2 flare images. But Neuromix also contains 2 3Ds. They're mostly single shot based, but it also contains 2 3D sequences inside Neuromix, SWI and 3DT1. And you can see that they fail. We do track them, they do update, but they do fail. But the rest of the sequences inside Neuromix don't fail. They are based on single shot techniques and they can survive heavy motion. And lastly, to the right, you see the T2 propeller, 2 millimeter there, is sharp despite all these 42 degrees of head motion. And here you can see all images from the same, and you can also see that even single shot techniques, even single shot here image, you can see that they drop out sometimes. You can see here from this one, this T2 flare, sometimes you lose a slice. This is because that motion, each slice plays out in a quarter of a second, and you have so heavy motion during that quarter of a second, so the slice is gone. There's no way to save it. But for the most part, the most slices are okay. And the bottom line is also that for radiologists, we have these like 6 types of contrasts, we have multiple copies of them. In Neuromix, there are 2 T1s, and then we have an extra T1. So we have maybe 3 different sort of candidates for the same type of image. So this is a very important slide. It doesn't look very important, but it is. This is from our study. How much did they move? On the top row, you see percentage. This percentage of scans, and a scan is like, we have like 5 to 10 scans per patient, and we have 62 patients. So we have a lot of scans, maybe 500 scans or something. All these scans, we had nodding motion in this direction, less than this amount of degrees. So if you look at 100%, you see 50.7%. For 100%, no kid moved more than 50 degrees, which is a whole lot. But you can see at 80% of the children move no more than 19 degrees. And 50% of the children move no more than 3.9 degrees. But what does it mean? Well, 30% bar at 1.6 degrees of head motion. This is roughly where normal MRI can handle it. Without you do regular MRI, somewhere here, if you just do regular MRI, about 30% of this patient with scan would have been okay anyway. And you should note that many of these children would have had anesthesia anyway. They would have had an MRI anesthesia, even though they didn't move in the end, without anesthesia. If you have 50% bar here, if you are saying, I want to succeed with 50% of my exams, I would need to have a motion correction protocol or an MRI protocol that can handle 4 degrees of head motion, which is pretty low bar, 50% success rate. If you want to be 80% successful, if you take all our children we have scanned, and you want them 80% of them to be successful, you will need to handle 20 degrees of head motion with your whatever way you do. We have done it in our way. And if you want to go for 90% success rate, which is sort of a nice number, because it feels like you're almost 100%, then you need to be able to correct for 27 degrees of head motion in this population. And if you want to be able to handle them all, we need to handle over 50%, 50 degrees of head motion. In our study, we have the question to the radiologist: after our MR protocol, does the patient need repeat clinical MR scan in sedation? Did our protocol, was it good enough for clinical diagnosis? Can we take the kid off the original clinical planned MR and anesthesia? And for the bulk, for the not needed or probably not needed, accounts for 84% or something. And here's 2 groups, age category less than 5 and +5, and we tracked them what happened to them. Well, for the 5-year-olds, most of them completed the exam and led to success. For the less than 5, before we started to introduce the preparation video to them beforehand, we had some that didn't want to go into the scanner, some that partially wanted to complete the scanner, and some that only went into the scanner with the parent. And we had some failures. We have 84% success rate. But the reason for failures is not so much the imaging. It's mostly because we didn't want to go into the scanner. And that was before we started to introduce this prep video. So I think I should continue to the prep video. There was 2 prep videos were made. One is going from the street to the, I did it, this is 5 times the speed up for you to not be too bored. But it's slower in reality. But you're basically showing a guy I just did augmented reality, and they have the nurse here, and it shows all the way from the street all the way up to the scanner. And so then this is exactly the path the children are going from the street, exactly to the correct doors, so they know all the way. And here's the second prep video, which I'm very proud of because it took me a whole week to do. I'm also very happy for GE for sending me the shell of the MR scanner. Thank you. So here's this is 2 times the speed up. But here's showing that this is exactly how it looks. We have palm trees. We have monkeys around in the palm trees. We have a mom or a parent next to the child. And then show all the procedures. So you show you the headphones coming on, and then we also have audio. Here's the rad coming on. And here's the coil and the squeeze ball and our homemade mirror. And then they can look in the mirror and see movie. They usually choose the Minion movie because it's the best movie. And then they start to take images. And then the mom is usually, and then it's pretty boring here at the end because the child should see that it will take a long time and that image will come. But we have had this, some children have seen these videos over and over again at home. It doesn't cost the hospital anything because just send them a link. And for those children who have done that, they just jump up and go straight in. It was amazing how much reward it was for this video. Totally underestimated. Study summary. It's possible to correct for 50 degrees of head motion, 40 to 50 degrees of head motion. Diagnostic quality, 84% of the exams we tried were successful, but that was also including the 6 out of 7 fails due to that we didn't have the prep video. 6 out of 7 of the case we failed was due to that the child didn't want to go into the scanner. So. Low latency, I didn't show it too much today, but we have a paper on that to the right. Low latency is a short time between motion happening and you can update the slices of field of view is key for large motion. I didn't show it here, but we did also scan vanilla Cartesian 3D gradient echo scans in this study. Each and every scan failed for all kids, so we gave up on that. It doesn't work to have this heavy motion with the 3D sequences. Largest reason for failure was refusal to go into the bore, especially under the age of 5. After prep video introduced, with no refusals, we got down the sort of convincing time, so please go into the scanner, down from 30 minutes down to 5 minutes, if that. Some children have even asked for the device, put it on their own head. There's a huge impact on prepping them. Last slide, brainmrimotion.org, a website I made for try to make the society to share motion trajectories that have happened in either volunteers or patients with different diseases or not. We have put up all our you can go in there anytime, and you can see how much they moved, each and every patient. So, and everything you can see is under Adam van Niekerk's name to the left there. That was it.